Okay, let's start the session. Quickly, let us introduce ourselves. My name is Alexander Frank from company Arconsis, and I'm mostly doing Android development, some backend development, and because it's now the hip topic, some machine learning.
Yeah, my name is Andreas Eberle. I'm also working at Arconsis. I was mainly working with the machine learning topic now, and I'm also doing currently my master thesis in this topic with the idea of person re-identification.
This talk we want to talk about our experience. Where we started from to get to a deep learning enhanced app with the knowledge we built up during this process, the mistakes we made, and maybe I want to share it with you, so maybe you could learn from our mistakes or get some insight and maybe get some inspiration. I don't know. First of all, a quick introduction to our company so that you know who you're talking with. We're a small company based in Karlsruhe and Stuttgart. Currently about 30 employees at that moment. Mostly doing work in mobile development and some work in backend development, some enterprise development as well. And then we're doing some machine learning stuff. So the focus of the company is mostly enterprise focused, so more of the doing software for the big companies in Germany, and mostly on the back end. But we are more and more getting into that deep learning stuff. So what we wanted to try to accomplish in our project, the project we had done was for a large company in the automotive sector in Germany, and they wanted to build a system that was able to recognize text on certain documents. So it was highly specific documents. So that we also could apply some domain knowledge to it, because we didn't need to identify everything in every document, because only you have to identify that one document. The interesting part about that was it was a more complex task because of the nature of what we have to scan. For example, we didn't have fixed fonts, or we hadn't fixed lighting for something like if you are scanning it with an embedded scanner or something like that, where you had fixed lighting that reduced the problem drastically. But we hadn't that because it hadn't be run on an Android smartphone. And that also means that you have to factor in shaky hands, something like that, or that the user is moving from certain environment to other environments, where sometimes you have the lighting of a conference room, sometimes you have the lighting of nature, environment, the sun, something like that, which also has to be factored into that.
And the additional problem was the document shape. It was in a really bad shape, or it can be in a really bad shape. This makes it additionally harder, because sometimes they are printed bad. They are not printed in the cells where the text should be, but more on the borders of the cells. On some parts of the document, there are not even cells on which you can orient yourselves. Additionally, some of them are in bad shape because they have been used a lot, folded a lot, or they have dirt on them. So, a lot of stuff that makes it tricky.
What was our experience prior to doing that project? Our experience was very little in machine learning. We acquired all the knowledge we now have during that project we've done. So it was some playing around with some basic net or having a lecture on the university, something like that. So really basic knowledge to start with. We had more experience in the traditional, more computer vision oriented programming, know about more the classical approaches, could more relate to that at the beginning of the project. We had experience in building complex enterprise systems, because that's what our company normally does. And mobile development. That's the main focus of the company. So the question for us was where to begin. And begin with something we know. At the beginning, we thought maybe if we have something like, start with an easy task, start from the scanned document where you can see if they have a nice white paper background and black fonts, then it's pretty easy to get hold of the text and extract simple letters and something like that to recognize them, because you can just, this is white, throw it away, this is black, we want that. So therefore we started with that, because that's what we know. And then after that we used Tesseract to train some fonts. And said to Tesseract, here is our text, please identify it for us. That worked for a certain amount of fonts, as long as it was a very small sample of fonts. But we realized pretty quickly we don't have a certain amount of fonts. We have like the whole spectrum of font. So everybody on that document could do what they wanted with every font they wanted to use. So that made it pretty hard with using the traditional approach.
Yeah, and we also started with the traditional approach because it's a well-understood approach. It's a major technology. It has been used a lot. The libraries are very good, and you can really understand it because if you apply a filter to it, you directly see the output. You can see what's the output of edge detection and so on. Because of our varying conditions and because we did not have a scanned document, we have an image done with a mobile camera, which can be bad. Tesseract and so on did not work, the out-of-the-shelf stuff.
So therefore we really pretty quickly moved to the next idea. And that was to incorporate artificial neural networks for the letter classification part. So that was more than the part we got the letters somehow out of the document. We had the single letters extracted, and then we started to build a neural network and classify the letters on that data we got. Our first idea was, because it's the basic hello world of the machine learning, to use the MNIST sample and the net they provide there, and just take our data and throw it into the net they provide there and see what we get for a result. Maybe it could be good enough.
Yeah, so that's how we started with the MNIST, and I think that's quite a good start if you want such a simple classification task, because it showed that it's best to start with a simple and easy network and then improve it by increasing it, because once you got something that's running, you can start improving it. But what do we need to actually start running it? Well, we need such an architecture, start with MNIST, and we need a lot of data.
Many data. So therefore, how to get that data? How to get that data? We tried different approaches. One of our approaches was at the beginning we didn't have enough data, so maybe generate some data in some random fashion to get more data out of it. This was the first idea. and then augment it or go to the more real data as we collect it.
Yeah, with generating data, we found out it can help at the beginning, but we were not able to really generate good enough data. This might be an example. So we used letters that we already had classified and labeled and combined them. Obviously, the background here looks quite different. We also had the problem that when we use generate a noisy background and print some font on it, the font is just too good. That's why we moved to that, because the real letters are just so bad and different. But still, original data was much better. So we really had to label all the data.
So how to get the real data from? Basically what we did, we created a small specialized Android app. Basically it was an activity that showed some preview, and you could then identify that it was that document we were searching for, and then set to the user here, please load up that picture to our server so that we get the training data. So that was first collecting the data. Because our first idea was, okay, we could also let the user of the app classify the data, but nobody wants to really classify data on an Android app, or they would throw the smartphone back to us. Yeah, it's a pretty tedious task on a smartphone, and it is much more easier to achieve to classify data on a laptop because you have obviously the physical keyboard.
Furthermore, it's also the case that a field worker is an expensive person most of the time, and you don't want to waste the field worker's time. We had the luck that they gave us the data by just making a photo, but that should not take, in the best case, not take any time.
Yeah. The difference why specialized app and not camera app, because we wanted to make sure that the person uploading the picture just didn't take a picture of his cat and load it up to us, but really we get the document we wanted to have. Yeah.
Additionally, this has the advantage that we get images from the cameras that we later want to use. They were the same phones used, and also they were used in the same environment. So this lightning problems, sometimes we have lightning outside, lightning inside, and so on. We also had all this variety in our test and training data.
So after we got some data, what should we do with that? That's basically a simple desktop app we created to be able to label the data, or that our workers could make sense out of the data we got. This simple sample, so that's not the real data we were working on, but just a sample. So basically what they were doing were they're saying here, that is in W, that's in H, and so on. And the important part of that is the task we just wanted to accomplish was make sense out of that's a W or that's an H, but it's not sufficient enough to just collect that data. You should also be aware of that, collect as much data as you can up front. Maybe you have some new ideas after that to do different stuff, or maybe other stuff with more machine learning.
Yeah, so the important thing is collect every data you get by doing this. You don't want to do it twice when you find out later, you should have saved that value as well. So this is only a part of the whole document, so better save the offset in the whole document of this part, and better save the coordinates of this bounding box in this part, so you can later reconstruct the position of the letter on the whole document if you need that later on.
And the next thing you need is a lot of human labor. So what we've got is got us some students, some pupils, gave them a laptop and said, here, classify data for us.
Yeah, and they went through like 400,000 letters, so they had to work some time.
Yeah, at least they had work in the rain. So. Okay, after we collected that, next step, what we did with the data?
You need more data. More is better, so data augmentation is something often used with neural networks to improve the data you have, to make the variations in the data even greater. So what you can do is like rotate the images a bit, shear them a bit, translate them, do whatever you want, make them brighter or darker, but do something that can really happen later on in the reality. So the network is training something that's helping it later on. And not like this example here, where the W is turned around, upside down, because we never have this situation. We always have the text top down instead of upside down. And if you train something like that, because you do too much data augmentation, you confuse the network, because now it looks like an M, and it should really be an M. This never happens in reality.
Yeah. So what I got out of it, so our starting point was something like 400,000 letters, the original letters, and after augmentation, doing that kind of stuff, lighting, rotation, what Andreas just explained, we went up to something like 15 million letters, so that we could train our network on the task at hand for recognizing and transferring the data, or recognizing the data and giving us the letter that's on the picture. So then the next step is to actually do the training.
Yeah, like I already said, better start with a small network, a known network, a network that you know it works. Because we use TensorFlow. With TensorBoard, you can have a look at the architecture and see what's happening, but you can always mix something up and wonder why it's not working at all. So better start with something that you know it works, and when you have that, start implementing the whole pipeline, and also start implementing tests for it. So you probably already have heard here or known before that you need a train and a test set for training neural networks to see if it starts overfitting. So you only train on the train set, and then you evaluate on the test set to see if it really transfers the learning, if it learns some abstractions. Important thing is we found out not only to test the network at this certain task, like detecting which letter this image is showing, but test the complete pipeline. Because before you can predict what letter is shown here, you need to cut out this letter out of the whole document. And we found out that's the more tricky part than actually classifying the letter. And it can also be that you're cutting out, for example, leaving some padding around the letter, and you always train the letters without any borders, only the letters, and then the network cannot really work with that data. So really do a complete integration test of the pipeline, automate these tests so you can run them very often to really evaluate, does it help when you improve the network, does it help when you change the data augmentation, and stuff like that.
Yeah. The integration part is most important because we pretty quickly got to a recognition on, I would
be interested what kind of feedback time are we talking about when we're testing neural networks?
How do you mean how long we trained our network?
How long does it take to get a useful test result?
Well, for the letters, so this train test set split, the test set takes like 2 minutes to predict. So it's like 30% of the letters. obviously without data augmentation, so 30% of the 400,000. And the integration test is not that huge. It's like 100 documents. And yeah, that's like 5 minutes running the whole pipeline, but only sequentially at the moment. We did not have the need to parallelize it. Yeah.
Really sorry, but I have to make a comment that makes me. So you say that you evaluated your model on the test. Is that right?
No.
Your parameters, you selected maybe the number of input features or the width of your conclusions or something like that based on the test results.
And we did the normal for the network training. We did the normal test training split. We trained our network on the training data, evaluated against the test data, and for the integration part, we had a validation set that the network never saw before, so that we got different results.
Mix the two names. It's just so you have to validate your algorithm on the validation set and test it at the end. It's quite confusing because in standard literature we switch to words. So you might give people the impression that you are optimizing your parameters on the test set. So
No, never do that.
That we don't do.
Yeah, because you need to see if the network really learns something for data it has never seen.
You are using multiple fonts, right?
Yeah.
Yes.
Yeah, right.
Real data, just everything we got, and put it in there.
Yeah, so basically the network itself pretty fast got to a high accuracy, something about 99%, but the integration part was the more tricky part. So with the pre-processing to get the letters out, so that was the more important part to test that, the whole pipeline, and not just only the classification part of the network.
Yeah, and obviously later on this was not only the MNIST network. We improved it a bit, but to improve it, yeah, you have to read some papers, or get some ideas what others are doing. For example, we were inspired by the Inception V3 network with its inception modules, and that helped us a bit. But it's not a big network. Still, it needs to run on a mobile. And on a whole document, there are a lot of letters, and so it needs to run a lot. And the detection should be as fast as possible.
Okay, now after we got some network and we did integration or some pipeline so that we can extract some letters and get to that point that we want to ship the trained network at some way. So what we used for training and for modeling our network is TensorFlow. We just used the capabilities given us by TensorFlow, meaning that we froze the graph. So yeah, throughout the training stuff, something like that. And
yeah, so for those of you not knowing TensorFlow as a background, TensorFlow stores the checkpoints, so the state of the model during training in two files. One file is the architecture of the graph of the network, and the other file is only containing the weights, the current state of the model. And for delivering the app, you usually freeze the graph, meaning you incorporate these two files into one. And yeah, then you can also do some further stuff if you need some more performance, like quantize the graph, meaning when you train, you usually use float 32-bit values, and when you quantize the graph, you can cut this down to int 8-bit values, which cuts down the overall size of the network by about 3/4. And it makes it faster to run because obviously, especially low-end, low-power devices do better with integer calculations instead of floating point calculations. So this can save you power on a mobile phone. This can gain you some speed. And to go even one step further, TensorFlow also offers to compile the network ahead of time. So you can really compile the whole network, that it's not interpreted at runtime, which is usually done when TensorFlow is running, but really compiled into the target architecture, so you can compile it for every architecture you have, and optimize it with that a bit further. We did this with one network. It helped a bit, not as much as we would have hoped, but this is still a new feature to TensorFlow. They are still working on this, so maybe they are also improving that in the future. One good thing about compiling is they can also do like optimizations like every compiler does. If you add a 1 and subtract a 1, something like that, you can optimize this and just leave it out. Yeah, stuff like that.
Yeah. So after we got that, we then put first of all we put the network we got into the app itself, so that we can ship the app with a network. Because when the user doesn't have Wi-Fi connection or something like that, that he really can start out of the box. So you don't want to first have to download the network from some server. That's why. But despite that, after we also put the network also on the server. Because after training iterations, something like that, after we improved, got more training data, so that we can push the network pretty fast to the users. Because in mobile, nobody or you have no control over the client, and you don't know when they will update the client. So it's probably the best idea to have some kind of update channel, so that you can download the network from your app and not rely on the users doing the app update. Yeah?
Say something about the stack?
How do you mean? What?
Yeah, coming.
Will come shortly. So first of all, the process that is running on the app. First of all, we had some kind of camera activity that was periodically getting the data or the image from the camera, and then pass it down to a document detector. Where we just can verify if it's the data or the document we are looking for, so that we don't get every picture and we don't run it through the whole pipeline every time, just to save us some computation. If we then have identified the document, we then went on to send it to an Android service that was running in the background, where we can do pre-processing. So that means extracting the letters, then classifying the letters, and after that bringing that all together, and did some kind of post-processing on that, in that we know what the document is, so we can apply some domain knowledge to better the result that we got. Document detection. Pardon me, I didn't get a better image of Cascade, so therefore here. But what we basically did was we used some Cascade that we trained with OpenCV to identify if it's the document we were looking for the first page of the document we were looking for, to be more exact, because there was some kind of special logo, and it's sufficient enough to just train a Cascade on that logo, and you can verify that's really the document you're looking for.
Yeah, the good thing about Cascade is it's finished stuff. You can just use it, but it has some problems with handling different sizes and cannot really handle rotated stuff. So for us, this was a good thing, because then we were also sure our document was in the right orientation and at the right scanned at the right distance to the document or photographed. So next thing you can do is, if you have some lines or boxes, you can do edge detection, standard or OpenCV stuff. Here we just used OpenCV to apply such a kernel to do edge detection like Sobel filter or something like that. And when you do this, you get back an image with only containing the edges. So then you need to find out where are the lines and to make some sense out of that. So for this we wrote some algorithms, standard stuff, going through the image, finding these lines, connecting these lines, because you can see there are some gaps in these lines, and yeah, connecting them to find out where's really the line, and then to be able to segment the document.
Mm-hmm. Still that stuff normally works, but also you have to compute it, so it takes some time, maybe not that much, some milliseconds, but you don't want to do it for every image. So therefore you maybe want to just do something like to know if the image is too blurry or something like that, so that you disregard the image right from the get-go, so that you don't waste any computation time, which can be done with some also some OpenCV stuff that's good enough for that task, or you can use something like the accelerometer of Android, so that you know when the smartphone is moving, the picture wouldn't be good enough, so you just can throw it away.
Yeah, an important part, like you said, is getting bad images out of the pipeline as soon as possible, because the longer they are in the pipeline, the deeper they get, the more time they cost, and in that time you cannot process the next image that might be better. And so you increase the delay when the user really has a good image and until it's really detected.
Okay, so what we then want to do is for pre-processing to then separate the letters. So as you can see, with varying conditions, some shadow over here, you're varying blurriness, so it's more sharp on that side, more blurry on that side, or even something like needle dot prints, something like that, where you still need to separate the letters from each other and don't separate the letter by itself. Where needle dot printing is not that good at. But that was the problem. We got all that variety, and we needed to somehow then separate the letters.
Yeah. Especially when you look at Q and R up there, you can see sometimes letters are closer to each other than the dots of a needle printer are together from the same letter. Stuff like that is really tricky. And as of yet, we only had this letter classification network, so we need to get the single letters, which is currently the hardest part.
Mm-hmm. So because our knowledge was more at the beginning at the CV part, we started with classical CV, trying to separate that stuff for something like if you have the raw image, try to do a binarization of the image, something like that. But what you can see here in the middle, if you have a shadow or something like that across the image, it's starting to fail pretty fast. So there are some techniques in CV where you can improve on that, so that you can still get a good enough image out of it, or a good image out of it, but not good enough. More like something like that.
You can see in the middle, the binarization is done with a fixed threshold of 128. So in the middle of the brightness value, but sometimes you have a dark image, sometimes you have a bright image. This fails totally. So then there's stuff like Otsu, where the algorithm is picking the threshold dynamically by looking at the image, but it still is picking one threshold for the whole image. And if you have varying lighting conditions in the image, for example, because you have the phone hold over the document and the light is on the side and you have a partial shadow on the document, then it still fails because it picks one threshold and on one part of the image it works, and the other part is just bright or black. So still, this stuff is tricky to use. You need to fine-tune it. We also tried applying it only on patches of the image, because then you don't have this large difference. If one side is very bright, the other side is very dark, and you only apply it on patches, you can get kind of rid of this, but on the borders, it's hard to match these images together again.
Mm-hmm. So next thing then you can try, or maybe try, to go to a different color space, something like that. You can maybe something get out of that instead of just using the normal RGB. Move it to an HSV color space and try to get some information in there to separate the letters, so that you get away some of the maybe there is too much green background on the document, something like that, that you can avoid that kind of problem. Would be an idea. Or an idea would be that we can then something like stretch the histogram of the image, so that we can just get the whole color space, or we can use the whole color space in it.
Yeah, we actually tried using HSV to pick on the colors, because usually there was a lot of one color in the background, but then we saw documents that had totally different colors. They were just washed out, or we got documents where the text actually had the color of the background, and yeah, that just totally screwed us up. So didn't work either. Yeah.
So obviously we need another solution, and that's when we came back to machine learning, to neural networks for a solution of that problem. And there comes in that we collected enough data at the beginning, so that we can go on and use a different approach, or a different preprocessing approach to clean out our data.
Yeah, what we here did is we wanted first to take this one line of the document. We were able to separate the lines quite good. So we took one line, put it in the network, and wanted to get out a line with better letters. For example, if you have a line printed with needle printer, you want to get out some normal letters, some good letters. But then, yeah, it didn't work quite that good, and actually it's not what we wanted. We wanted to get a solution for finding the letters, for separating the letters. So we came up with just transforming the input image to such a boxes image. Obviously, in real life, the boxes are not that sharp, but they are quite easily then to separate with standard object finding stuff. And maybe you add some padding to the box to make sure you have the whole letter. And with this, you can really improve the letter segmentation.
Yeah, so basically normally, as you already heard on this conference, you use that autoencoder so that it trains its input again, so you get just a representation out of it, but in a more unsupervised way. But what we just did is use it in a more supervised manner. So we know that is the target we wanted, and that's our input. So we then trained. Tried to force the network to learn the transition between the normal letter and the box, so in a more supervised kind of way, which worked for us pretty good. So obviously it was more suited for accomplishing the task than the more traditional approaches. So therefore we were able to get rid of most of the traditional CV-oriented stuff in our processing pipeline, and just ended up with using the autoencoder approach for our pre-processing to clean out the data, and then move on to recognize the separated letters. For the recognition task, you obviously
We did not use such a network. We used obviously CNNs, convolutional neural networks, because they are really, really good for image recognition. What's important for practical usage, you don't want to feed in single images all the time. Obviously, we want to use batches of images also on the mobile. Finding the right batch size is something you need to figure out for different device sizes. But this can really, really improve the speed. Yeah. I think, as already said, we were a bit inspired by the Inception architecture, got some stuff from there. For the autoencoder, we read some other papers to get some inspiration for that.
Mm-hmm. Okay, so after that, then the post-processing had to be done. Basically, that was or is still common stuff that you can do, like filtering out invalid letters. So our network was also able not to say this is A to C, or it could also say that's a blank or that's failure. So in case the autoencoder still made an error, we still can throw out the errors with the other network as well. And recognize that the part he did cut out wasn't actually a letter. So therefore, after that, filtered out the invalids so that we just got the letters and the numbers that we wanted. Until now, we don't have any white spaces, something like that. So we fill in the white spaces where we know them because of the mean size of the boxes in such a section. We can infer how big has to be a white space, so we can just insert a white space in there that we get the words out, and then apply some domain knowledge to the document or to the sections that we know from the document. For example, if we know that's an address, run it through an address detection, just to clean that up. Or use some kind of checksums if we know there are checksums in the document, so that we can know that the result we got is really valid.
You use some dictionaries, libraries?
We don't use the address dictionary stuff in our app because the customer is doing it on his side because he already has it there, but they use dictionaries for address stuff.
How do you know there is a white space missing?
A white space missing. We have a look at the gaps between the boxes we found with our autoencoder and letter detection, and then we see, oh, there's a big gap. So where there's a big gap, we just insert a white space.
The problem was we weren't able to use a dictionary because it weren't actually always words. There were also some technical identifications where you can't use a dictionary.
Yeah, and sometimes you have the case that in this field there's a word without any numbers, so sometimes the network confuses a 0 with an O or the other way around, so then you can fix it. Or sometimes for dates the dots are lost because they are quite small, so when you find this format you can say, okay, this could be a valid date, just insert the dots.
Okay, so that was in the whole pipeline we created. So after we created it, we also had to consider in the speed, well, maybe not after that, but during the process, during the development, not only after that. For example, for our approach, one constraint was from the customer that we had to use Java. So if somebody is now offended because we use Java for algorithms, sorry, was the constraint of the customer. But for our case, it worked well enough.
Yeah, and this is one thing is you can do algorithms with Java and they still run quite fast. It's not such a pain. The second thing is the really heavy lifting is done via OpenCV or TensorFlow, and they both run in native. And this brings with it some dangers. For example, when you run the native stuff of OpenCV, you always have a chain I call when you call it from Java, and these chain I calls, they really cost. They cost a lot, and if you do them a lot, you will feel it. And what's especially dangerous is like looping over an image, and in the loop you always check the width and the height of the image, and you always query it from the OpenCV image, and it always makes a chain I call down to native to get this value, and then you will have a slow algorithm. So stuff like that you need to query once before the loop and then use it. It's stuff like that you just need to care about. And if you still have some slow stuff, profiling always helps to find out the hotspots, to find out the parts you really need to look at. But we didn't have so much to optimize to really get it running smoothly.
Okay, so just to bring it all then together, how does the whole picture look like? So basically on the left, the big green box is the Android app. We already saw the pictures. The only thing that changed now, we swapped out the preprocessing, used the autoencoder we just showed, and threw away the more traditional stuff, so that we got that processing going on. And what we then did is we still now have on the client side of the app, when the data is displayed to the user, he still can make some corrections if he sees it was misclassified or misrecognized. And when we notice he makes some changes, we then just upload the data that he used for getting that to our server, so that we just can generate new training data. That we then can be used to push down to our human classifiers, to the program where the pupils and students were getting some of the suggestions from the server or from the neural network, the processing pipeline, and just doing corrections on that, pushing them back to the server so we can train a new model with that. In the beginning there was a lot of human labor to be done, but now it's just look over the data more or less and maybe just do a small correction, because most of the times now the processing pipeline gets the correct result out of that.
An important thing was also with the human labor, better double check it because they make a lot of mistakes. One thing is they get tired after doing this for some hours. Another thing is sometimes you just make the mistake, you send it too early. Sometimes, you need to overwatch it because they drift away from the way you doing it a bit different from the way you want it to be done. So we incorporated a review system, so where just another one sees it and can double check it. Because at the beginning we really saw a lot of some percent of misclassification, and if you want to train your classification network to get at 99 point something percent, and you have like 5% of misclassifications in your training data, you won't get there.
Yeah, and after that, after enough data was collected again, we did another training step with our network or our networks now, and push the new networks to the client so that they update itself. Mm-hmm.
How do you decide when to unfreeze or freeze something? Do you have some thresholds?
Well, like I said, we have this integration pipeline, and then we run it. We see the overall complete result, and we see, well, it's now 2% better, the overall prediction, then ship it. If it's worse, fix it.
Yeah.
How did you create the labels for the output boxes?
Yeah.
Well, basically, that was the classification software that you showed you. They didn't only record that letter was in W or something like that. They also recorded on that is the box that the user drew, and so we can generate data out of that. Mm-hmm.
Yeah.
Mm-hmm.
The other one is scan text like this, and I think they use it to do like to collect the data. The user can type, and then they can collect like data from training or something like that.
Yeah, well, the data we used for training was personalized data, so there was some also names and some stuff of that. So we didn't want to publish that on the internet.
Basically, you cannot. The law is there, and it's the data of of the customer, and you cannot just put this on the internet.
But if it would be some sort of unpersonalized data, sure. Yeah.
I mean, Google does it.
Right. Okay. So,
yeah.
More questions.
I'm very curious if you tried out several, these days full of crazy type fonts.
Yeah.
And, leaving all the rules that fonts are following, and or even the lead way of writing things. Like using some digits for some letters and so on. Still in the same context. Did you try out things like these? Did you see what results you get?
No, because we had these documents, and although they really use crazy fonts, for example, at one, we once saw a needle printer font, because the guys that printed that thought needle printer is cool, and they got a new printer and not a needle printer, so they developed a font that looked like a needle printer. But still, we only had the interest to get this running for the customer and not test it on something weird. But you could optimize it in another direction. But it's not a general purpose solution. It's a customized solution for this problem. Yeah, sure.
Okay, any more questions? How long did it take?
1.5.
Yeah, 1.5 years, something like that. So it was our period for 1.5 years.
But as we said, we started off with like little knowledge, and we first tried out another deep learning framework, DL4J, Deep Learning for Java, because we had the Java constraint. But luckily, then TensorFlow came out and saved us. It was much faster at that time already, and the development of TensorFlow is really awesome. How fast they are progressing. Sorry?
Because so what we saw was it weren't because of the technical aspect that we didn't have like a word, something like you have or whatever, because there was something like technical, also technical IDs, something like that. So then we tried that, or maybe it was a lack of knowledge. We learned a lot during that project. So that's why what we started with and what we came up with. Yeah.
Has somebody thought in the customer about getting rid of the document and
They are forced upon them. Yeah, they cannot do anything about it.
These documents are mandatory, and so they need a solution.
Yeah, that was like
Our first approach when we got the, or our first idea was when we got the project, just put a QR code on that and you're set. But yeah, you can't just do that.
yeah.
Yeah.
Can you use this both on Android and iOS for exchanging the model?
The model you could use on iOS as well. TensorFlow is able to run on iOS, but we didn't develop it for iOS. What you would need to write again would be some algorithms we use and so on that we wrote in Java. Yeah, the models can directly be run on iOS.
Okay, yeah. Sorry, you.
Compare your results to OCR engines like Tesseract or Genie?
Yeah, so Tesseract we tried at the beginning and it failed.
For that task, yeah.
Yeah, we started with we saw 5 documents. They look okay. We got 5 good documents. And then we were told there's 3 fonts. Then we got the 6th document. We had 4 fonts and so on. And Tesseract you have to train on fonts. So this failed. And we also tried the Google Cloud APIs once, which is a general purpose solution. And yeah, they went really bad. But it worked good, but not good enough for the client. Still impressively good for a general purpose solution on this tricky field, but yeah, you need to really customize it and use everything you know about that stuff. Yeah. But still, every time you use something, you find out this knowledge is not true.
So you had a question? Okay, good. Okay.
Any more?
If there's no more questions, thank you for your attention and enjoy your lunch.